you need to accept the recording. Okay, so let me share my computer screen again. Yeah, okay. Yeah, okay, so today we will focus on to building the split-Hopkinson pressure bar based on the dynamic uniaxial complex of strength test for the 3-dimension. Okay, before we introduce that, I think, yeah, so thanks to Duanyang last time send me the Dan model. Yeah, so yeah, Mark mentioned that actually it's challenging for our FPA to deal with the button with this size. I think that we have about 1.8 million of the elements. Yeah, I think that for our code, that's no problem. Using the model, Duanyang sent that to me. Yeah, so then I put that into our code. Yeah, so then we can run. Yeah, yeah, you can see here, this is involving a huge number of that in the element. Okay, related to this model, actually, I have many of the questions I wanted to ask Duanyang. Okay, I will ask that later during the discussions section. Yeah, I wanted to know how we apply that the loading of the conditions. Yeah, how we apply the boundary conditions. Yeah, okay, we will come back into this later during the discussions section. Okay, so let's focus on that in the tasks today. Yeah, for the dynamic uniaxial complex test, which is similar to the dynamic the dynamic predominance test, which we introduced in the last time. What we are building is that the same of the loading equipment. Yeah, I think that at this moment the rock dynamics, that's a hot topic in the field of the rock mechanics. Yeah, we know that recently we have the rock dynamic 4 was held in China University of that Mining and Technology. Yeah, I think that's a few of you submitting the papers there. Yeah, in my group providing your presentations and where also that the paper was written by my former of the PhD students. Then is presented by the my collaborator Daisuke Hokuda in Japan. So you will notice that recently the Rock Dynamics Committee for the International Society of Rock Mechanics and holding a series of the presentations as well. Yeah, so that's for the younger of the researchers. Yeah, it's our group providing one of the presentations there as well. Okay, so we have that in this actually is the standard equipment. I think that now many of the university have this the laboratory equipment. Okay, what we are building here, yeah, is using that in South Korea university, and actually, so that's the same as that like that in the Monash University. Okay, so here I using that in the figure. Yeah, so that's show the schematic sketch of the experimental test system is using that from the South Korea. Actually, so the experimental data, what we are using that is from Monash University. Okay, so for this system, so we have that in the input bar, then the sample, then the transmissions bar. Yeah, so then for the experimental, so they were using the high speed of the camera here. Yeah, obviously for the numeric simulation, we do not need that since we can capture each of the time step. Yeah, but we do need to put in that in one of the Boolean point, one of that's in the incident bar, and then the other one, so that's in the transmissions bar. Okay, so then we build in that in the border license of this. So then we put in an impact here. So then the impact which will cause the stress wave. Yeah, so then which will fraction of the sample. Okay, so firstly, let's look at what is the Bodine's results. Yeah, I actually showed that that's lots of time out where you can see here. Firstly, we have the stress wave propagation in the incident bar. Then when reaching the sample is highly stressed. Yeah, you look at that, almost that's the identical column. So that means highly stressed. So then after that, with the stress wave passing away, so then we have that rock sample, which is fractured. Yeah, you can see this is actually getting very complicated of the fracture pattern. Unlike for the static unit X complex phase, we know in the laboratory, according to that's the Berkeley zero, we were getting a single of the shear plan. But for the case for the dynamic of the unit X complex phase, so we get in the complicated Fed pattern. I think till this moment, this Fed pattern, yeah, is still not well studied. I think for your case, yeah, you can use that in the setting of the model, which I will share that to you. If you using your own experimental data, you just replace, change the input parameter and change, so that's the impact which is correspond to your loading of the system, yeah, then I think that you will be able to write in your paper about this. Yeah, so for this one, for the dynamic resilience test, I have already shared that in the data in Cincinnati's computer. I just looking on Cincinnati's computer before I starting this presentation. Yeah, I set in that in the model, the dynamic BTS model in last week. Yeah, I think that's, yeah, although since his computer is not very powerful, yeah, but that's the is reasonably to compare of completely of the calculation. Okay, so Tintin, if you do not mind, I can log in on, I want to log in on your computer. So then I see. I show everyone how that the results looks like. Okay, so I will log in on Tencent's computer. I will using that in the remote control of that software. Yeah, okay, so please bear with me for a minute. So it takes some time to log in on the remote of the computer. Yeah, you can see here, this is that's the what we introduced since last time on Tencent's computer. Yeah, so although this is a graphic card which is not quite powerful, but it takes some of the time to do the modeling. If we trace the results, we can look at that and how long does it take us on Tencent's computer. I think that's in the GTX of the graphic card. Okay, we starting to do that in the modeling. Yeah, so which is 13. Yes, around that's in the 7 o'clock. I think that's in 7 o'clock in the afternoon. Okay, so then we have that in the 14th. Yeah, it's not too long of the time. I think that's just around the 24 hours. Yeah, but actually, if we have that using powerful of the computer, like the computer on which I am currently using to deliver the presentation, so I have this is that's in the GV100 of the graphic card. I think just needed to take one latch, which will complete in the calculation. Yeah, I think that's for your case. Yeah, if you, yeah, idea of the case if you do the laboratory test as well. So if you do the laboratory test, you just need to replace this the rock sample, since we have that in the transmissions bar and the incident bar. Actually, this is the standard. And then, yeah, you can change this and that in the impact. So then you will get in the full set of the results in which we presented here. So then you will be able to publish a quality of that in the paper. Okay, so let me stop into using Tencent's computer. Okay, so let me. Okay, so then let's come back into this presentation. Okay, so for this model, yeah, it's quite challenging. So actually, you may notice that actually we, by doing the dynamic BTS and the dynamic UCS, we published 2 papers about this. One of that, so we published that in the rock mechanics, rock engineering. So that one, which is focused on the comparison with Monash's experimental results. And then the other one, we focus on the how we model that. Yeah, is focused on that the development. So then that one, which is published in the International Journal of the Rock Mechanics and Mining Science. Yeah, we know, yeah, in our field, both of that in this journal, so that's the top journals in our field. Okay, so why? But in this simple of that test, we can publish 2 papers. So they have a few of the challenges there. Okay, the first one, the challenge is that, so you notice that for our case, we model the whole of the SHPB system, except this is the striking bar. We didn't model the striking bar. For the striking bar, so what we directly, we given that an input file, so that's pressure, and that's time of the profile of that input file. But for the input bar and the transmission bar, we model that in the flow of the system. Yeah, so then in that case, involving a huge number of that in the element that's there, then in that case, if we do not have the parallelization, so it's impossible for you to do that in the modeling with this scale. But actually, so if we consider that in the parallelization, so this model is still not too big, yeah, which is only about the 0.4 million of the element. Yeah, as we said, so even for the DAM model, we have 1.8 million, we can model that. So 0.4 million is just a piece of cake for us when we have that in the parallelization. Okay, then the other one, which we did that's different from the traditional. Okay, so for the traditional FDEM, for them to do the modeling, yeah, as we know, for the FDEM modeling, so we involve into that. So after the failure, you were involved in that in the, which is the contact. So before that failure, what we have that's the cohesive element is bonded together. So then in that case, there is a transformation, which is from before of the cohesive failure, cohesive element failure. So what we use in that, which is the cohesive bond of the force. After that failure, so then what we use in that, which is the contact detection. Then in that case, which is involving a transition. So when you have that in the transition, yeah, so I will introduce that and why that one, which is difficult. Okay, I have that. If we look at that in this figure, you can see, yeah, I focus on this is that in the red part is show the sample, and here this is that in the blue part is part of the insider bar and the transmission bar. Okay, the first one, what I showed in that, which is for the traditional of FDEM, so like that using that in the other group. So like that in the China group, yeah, I think the China group FDEM, the basic one at this moment is that Professor Yang in Chinese University of the Geoscience. I think that's Wuhan University did a little bit, and that's Institute of Mechanics in Beijing did a lot of work in that as well. Yeah, both of that in the group, so they regarding this, which is we call it that in BCAA. Yeah. And for our case, we what we call we using that in ACAA, semi-ACAA. So the difference is here. You can see For our case, we initially only have the contacting that happens here. Then for our case, we only activated the contact calculations there. Okay, I can use that in another of the figure, which demonstrate this concept, which is clearly. Okay, this is 3 of the scheme. We call that the brutal contact activations approach. We call that BCAA. And then the second one we call it ACAA, which is the adaptive contact activation. And then the third one we call that the semi-adaptive contact activation. Okay, why we have this the different scheme? So the first one, so as we said, when we do the FDEM modeling, so we have that the tetrahedral element. Why we are able to model the fracture, that's because between of the tetrahedral element, we insert in the cohesive element. Okay, for the 3-dimension, which is CE6. Okay, for this cohesive element, so before that's in the fail, so what we should calculate in that, we will deal with that as using that in the called the cohesive bond rate, or called the repulsive of that in the force. Okay, after that failure, so then we have this cohesive broken. We will transfer this that's contact. So then we were using the contact mechanics to do the calculation. Okay, so for the transitional of that in the FDEM, that's no matter if you have that failure occur or not. So we can simultaneously apply that's the cohesive force and the contact force. Yeah, obviously in that case, we wasted a lot of the computational capacity. Okay, so then which is have that in the purpose that called the ACAA. So then in that case, only around the crack. So then we put in that in the contact. So then in that case, we can delete. So the bonding stress, then we completely using the contact force. Okay, so this is that as I introduced before. Yeah, it works well for that the static of the body, like in that, yeah, I introduced before. Yeah, we published a paper about this one. So in the computational particle mechanics. So for the static test, it's well, but for the dynamic test, so this will have the problem, which will cause the spirals of the failure border. Okay, why is that causing the spirals of the failure border? We spend a major of the effort to try to understand of the problem. I think that this is related to the fracture progress zone. So we know, yes, like that in the RFPA, we call that in the rock failure progressive of the failure. So why we adding that in the progressive, that's in the terms there. That is, yeah, in the rock or that's in all of that in the breach material. When we have that in failure, we have a fracture progress zone. So you won't really have that in the immediately, so from the intact till that's in the failure. So you have that in a fracture progress zone. And this fracture progress zone, during your modeling, so you deal with that's in the carefully. That's the from that's macro damaging till that's in the completely of that in the failure. Okay, so for your case, if you have that in the crack, which is formed here, although for that in the adjacent of this crack or that's in the front of the crack, so you have that, so has not completely failure yet, or we say the damage failure, which have not approaching to 1, but you have that already bigger than 0. So have that macro damage there. Okay, if that's macro damage, if you do not deal with that, so then which will cause the spirals of failure border. So what we do is that, so we around that's the macroscopic of that failure. We consider a zone, and for this zone, we simultaneously apply that's the boundary of the stress and that's the contact of that the force. So then in that case, we can gradually reducing the computation capacity. So that's why we say for our case, we are able to model a bigger of that model. Okay, to explain this more clearly, so what is that the difference? Yeah, I draw that in a two-dimensional of the modeling. I show that, yeah, although we have this problem, actually is three-dimensional. I simplify that as the two-dimensional. So we have that in two of that in the tetrahedral of that element. We insert of the cohesive element. Initially, so we have this cohesive element is zero sequence. So that means so this load actually which is overlapped with each other. Although for the visualization purpose, I draw that in the 2-point at the center of the location. So we look into that. Okay, for this transitional of that in the FDEM, so what we do before we have that in fail, so we apply that in own repulsor of the force due to the cohesive element, and also apply on a contactor of that in the force here. Okay, when we have this is completely broken, then in that case, so we only apply for the contactor of that forces there. So then let's look at that in adaptive contactor activations approach. For that one, before of the failure, okay, we only have that in the cohesive of that force there. Then after that, we have that in the failure. So then we have this is applied the contacting force there. But you can see here, this way involving a certain of that changing. So you have that from the cohesive force becomes of that the contactor of that the force. Yeah, so, but for the rock failure, so we say we have that in the fracture or progress zone. So then in that case, so then there is a problem. When we need to do this, the transition from the cohesive repulsive force to that the contact interaction of that force. So we need to control this carefully. So if you do not control that carefully, so then which will cause the spurious of that failure pattern. What is called the spurious is that like in the explosive, as long as you're loading that in the sample everywhere, so that's a fail. Okay, so we try to understand what is that in the mechanism. Yeah, obviously, so that does not happen that in the opening, the mode one. So when we have that the opening, so it completely separated each other. It does not happen that due to the contacting. So due to that contacting, since we have that in the contact force, which were proven that in the penetration. Okay, so why does it happen? We actually did that in the careful study. We found that what happens is that in the shear softening of this stage. Yeah, what cannot happen so that at this stage, since at this stage, so we can prevent that overlapping. But for the shear softening of the stage, okay, so we have that in the cohesive force, so which is continuously decreasing. So decreasing, then you want to prevent that that's the overlapping, or that's the unphysical of the overlapping, unphysical of that the movement. So we have this study, this is that state of the cohesive force. So we have this sample which has not completely failure yet. We say, so after that's completely failure, then in that case, we were putting that in the contact force. But at this stage, so we have this has D is not reaching that equal to 1 yet. So then we have not activated the contact calculations yet. So then you can see here that way causing that the severe of that the unphysical movement. And this one, which we're causing the problem. So as long as you activate the contact there, since this has already have significant overlaps there, so then that means when you activate the contact force there, you will suddenly have a very big of the contact force. This suddenly of the big of the contact force, okay, so which will making everywhere becomes that's unfair. So then you're building, which we're not building that's in the physics. Okay, so what we do is that, okay, we control that in the timing of that in the activated the contactor. Okay, so what we use in that, that's the semi-ACC AA. We say adaptively activated contactor for tetrahedral element in the closed vicinity of the cohesive element, which enter the shear softening with FD, so dropping to a threshold value. Okay, so later, what I introducing that, so I introducing that in an FD. Okay, so which is control depends on at this stage where we activated the contact. Okay, so that's the next one. Okay, so here this is actually shows that the three different sort of scheme. If we put in the dynamic uniaxial compressive test. Okay, you can see for the first one, if we using the adaptive contact activation, due to the previous of the problem which we mentioned there, so you won't be able to physically burden that in the failure pattern. So what you get in the results, which is always lacking to the, oh, sorry. So it's always lacking to this. So you get in that everywhere, so that's fair. So if you have that in the experience to do the laboratory test, so this is not that in the physical. Real of that in the physical, so happens in that in the laboratory. Okay, so then we using that in semi-ACA back control this threshold. Okay, so this threshold that we put in that in D equal to 1. Oh, sorry, so this is differently equal to T. Actually, so that's D, which is justly is starting bigger than 0. Justly is starting because of the strength of the, or correspond to, that's in the previous of that in the figure. So actually, so what we do is that, so we activate the contact calculations here. So justly enter that in the strength of the. Okay, so for that case, you can see, yeah, we can reasonably to model that's in the failure pattern. Yeah, but we save that in the computations of the cost. They feel the computation cost for the brute contact activation. So that's at the beginning of the calculation, activated in the repulsive force and the contact forces everywhere. Okay, so then by all the jaws, so this threshold to the differential value. So then we understand that why this speediness of that in the failure border, which is happen. So you can see here when we have that in the threshold, which is quite close to that 0. Okay, this is threshold close to 0, which means this D, which is approximately, so that's equal to 1. So that's when we have that completely broken. So that's more close to that's the adaptive contact activation. So that's the ACAA. Yeah, so later I will introduce that. Yeah, if you using the different value here, actually, so that's the calculations time, so which will be different. Okay, so besides that, we have that overcome the experience of that in the failure border. And we also noticing that which is causing more reasonable of the stress wave propagation. Okay, so you're looking at an ACA and a semi-ACA for the stress wave, both of the case which will have very good of that in the stress wave propagation. Yeah, but for that in the BCA, due to the simultaneously apply of the repulsor of the force and the contact force, actually, so you get in some of the noises here. Okay, so then the other one is that show that in the speeding up. So the scheme which we are proposing here is not only overcome of the problem, which is improving the stress wave propagation. More importantly, which is improving that in the calculations speed as well. Okay, so let's look into this one. Yeah, so we comparatively that's we for the for the BCAA case, the transitional case, we regard that as one. So you can see due to we apply this scheme, so we achieve that yeah, so above the 80 times faster. Oh, yeah, so for this case, obviously, so that depends on how many of the elements are there. If you have more of the elements there, then you have that the time of the speeding up, which will become bigger. Yeah, but if we look at this figure, you notice that initially, so have a good of the speeding up of the times. But with the calculation, yeah, then you can see if we have that the ACAA, BCA is correspond to equal to 1. And then this one, which is only equal to 1.2. Okay, 1.1, 1.2. Okay, so here we have this just 1.2. But on that, at the beginning of the simulation, we say, okay, so this is 1, 2, 3, 4, that's 10. Okay, 11, so 12, so 11, I think that's 20, 30. Okay, so that's about 30. I think this is about 40 or 50. So you can see that initially we have a good speeding up, but during the later of the staging, so we have the speed of the time, which is quite small. Why? What is that reason? So that's from when we activated the contact calculation. Okay, so during the later stage, we know we have that the macroscopic of that failure occurs there. And then in that case, since you have that failure occurs there, so you need to activate the contact calculations at the location of that failure. But initially, since you have that the elastic stage, at that time, you do not have any of the failure there. So then in that case, it's unnecessary for you to apply the contact forces there. That's why initially, so you have a bigger of the speed of the times, but with the calculations progress, so you have that the speed of the times is not so big. Yeah, but that's still big. So 1.2 times faster. So it's still, that's quite big. Reasonable, that's the results. Okay, so that's what I introduced in that in the background, introducing that the zero. So while we have that in the, for our case, we consider that in the full of the splitting Hopkinson of the system. So while our code, which is besides of that in the parallelization, while our code is even further or faster, so then that's an other group of that in the code. Okay, so now let's come back into the practice and how we using that in HFDEM to model the dynamic of the Unix complex test. Okay, so here that's again, yeah, so we needed to use the HPC version and instead of using that in the GUI version. Actually, it's a GUI version. So since 2019, so we didn't do any of that further of the development. Yeah, so since with that the calculations model becomes bigger and bigger, so then the graphic using the interface of that version, which is becomes less and less efficient. So we using, yeah, so for you to do this modeling, so you need to use that in the HPC of that's the version, either of that in Linux or that's Windows. Okay, so the procedure you can see for all of my lectures, no matter what kind of modeling, I always follow this procedure. So building the geometry, building the mesh, specify the boundary conditions, material condition, and then specify control parameters, then the visualization. Okay, again, first to build in the model. Okay, I use that in the upcursion to build in the model. Okay, so the model, what I built in that, I will not show that. Yeah, I will just visualize the model which we built into here. Okay, so here this is that's a global of that in the view. So we have this is that in the, yeah, I think that's this is that in the input bar, I think that's in the standard one, which is 2.5 meters. Okay, so then that's from here to here. So this is the transmission bar. The standard is that's in 2 meters. Okay, then we have that in the sample is here. Yeah, obviously since this big scale, so you can see nothing of the sample. If we zoom this part, okay, if we zoom this sample, okay, you will see here that we using that huge number of that element here. And for the Hopkinson bar, what we concern is that since for the other part of the Hopkinson bar, we are only modeling the elastic behavior. And for the elastic behavior, actually you can use very close of that basis. Yeah, so windily reducing the accuracy of your calculation. Yeah, but that's the important thing is that all right. Okay, so we have that. Yeah, it's difficult for you to see. I think this is that's in the boundary. And here, this is that's in the boundary. Yeah, so all right, the sample, okay, we put in that in quite a dense of that information to there. Okay, so for this one, I think that is better for me instead of show that in the component presentation. So I show that in the articles. Okay, I show, yeah, repeating what we do that. Okay, firstly, I deleting this one. Okay, we say we starting not from the building the geometry. We starting from the input file, the IMP input file. Okay, for your case, I have already prepared this IMP input file. Okay, so this one. So this is that I save all of that in the input file here. Each time after my presentation, then I will transfer this file to Tinsyn's computer. You can find all of these files on Tinsyn's computer. Okay, so for this one, I already building that in the geometry, building that in the input file. Okay, so this is that in the input file. So what I do is that I use the opticals to visualize this input file. Okay, so then I goes into opticals. Okay, then I input in that in the input file. Okay, so this is that I already copied that into here for my convenience. Okay, so then I open this one. Okay, so the advantage is in the input file is that no matter the version of your opticals, yeah, you will always be able to visualize that. Just like in the dance model, yeah, for the dance model, yeah, Duanyang, so firstly send to me that's in the CAE file and ODB file. Yeah, but since our computer, we have that in the differently version of the opticals. Actually, for that one, I was unable to look at that. And that's why I asking Duanyang send me that's in the IMP file again. Yeah, thanks for Duanyang for that's in the IMP file. So then I'm able to visualize that and then putting that into our software. Okay, so looking at that, okay, let me zoom this part. Yeah, so you look at that in here, so we have that in, or you using this one, the visualization. Okay, yeah, you can see here, you can clearly visualize into that. Okay, let me, yeah, so this part, so that's the rock, and then the other part, so that's the split-Hopkinson bar. Okay, so let me remove this the rock sample. You can see for the Hopkinson bar, although for the all of the locations we using that quite close of the basis, but around the contact we using the dense basis. Yeah, so why we needed to use that in the dense of the basis. So what I suggest you to use for this one is that to use which is closer, almost that's the dense of that's the meshes. Okay, so let me add in this back. Yeah, so we making sure this contact surface on the two sides of the contact surface, so we have the element which is have almost that's the same of the density. Okay, so this is that's important for the accurate of the contact calculation. So we know for our contact calculation, so we using that in the penalty. So the contact, although we have here, this is that in the surface between of the bar and the surface of the between the rock. So we finally will discretize with the contact between the tetrahedral element. Okay, so you need to make that on that's the master, or that's level, or that's the contact, or that's the target. Okay, if we using the obcus term, yeah, obcus term, which is using the master and slaver. So you have that's the master and slaver, so which will be crisp. The element in the density which were closer to each other, then in that case, which way you were getting the accurate of the contact calculation. Okay, using that in the FDEM term, we using called the contactor, and that's the target. Okay, so this is that in the building the model. Okay, so the model, yeah, if we look at that in the input file, okay, the input file which looks like this, so you have that in the bar, and that's in the rock sample. Okay, so what we have here, that's the node coordinate, and that's the element, the connectivity. Okay, so here I already introduced that many of the times. We say we just directly need to copy this data, okay, to form a file, to form an input file, okay, which is this one. Okay, I already did that. Okay, so this is that in the structure. Yeah, so let me briefly review this again. What is that in the format here? We introduced this many of the times previously. We say the first one, so that's the total number of the elements. So here we have the multiple of the parts. So we have the parts of the rock, and we have the parts of the bar. Okay, here that's the total number. So that means the number of the element for the bar added the number of the element for the rock together. So that's the total number of the element. And this one, so that's the total number of that nodes. Okay, again, that's adding together. Okay, here we have that's two parts. Okay, here that's the first part, so that's the rock sample. Okay, then that's the what is the total element for this part, and the total number of that nodes for this part. And then this is that similar to our course, this is for the translation, and then this is for the rotation. Okay, so here, since that we can easily to use our course to use that. Actually, although we have that development function here, we read on use, we always put in that equal to 0, since our course is a much more of that's convenient for you to operate the code if you needed to move something or rotate something. Okay, here that's what we copy. That's the connectivity. So that's the course in the MP file. So we copy this data. So then we paste it there. Okay, so that's the element. Okay, then after that, so that's the node of that in the data. Okay, so this is just the copy that Abacus's data. Then for the second one, then the bars. Okay, for the bars, what we have here, we have that, although we have this, that's in the multiple of that in the parts here. You look at that, and so this is the input bar, and that's in the transmissions bar. Actually that's separate. We regard that as a single of the parts. Yeah, of course that's okay if you regard that as a separate of the parts. Okay, we regard that as a single of the parts. So then you will have the total number of the element and total number of the nodes. So again, we copy, so that's the element connectivity, and that's the coordinate of that. So then we put in that into this file. Okay, so this is that for the node coordinate and element connectivity. Okay, so the remaining, what we needed to given that, we given the initial condition. So we given that the velocity, initial velocity, so that's everywhere, so that's 0. Okay, so then we given that in the element property. So then we given that in the loading property. Then we given that in the load boundary flag. Okay, so for this one, okay, so we were using that in C+ program. Okay, so for that one, before we go there, so let's look at that in the definition. Okay, what we make that in the definition is like this. Okay, so here, for our case, we have that in the rock sample, then the input bar, and that's in the transmission bar. Okay, so what I will define, so I will define that in the rock. Okay, we define that in the materials ID, we define that as 0. And then for the input bar and the transmission bar, so we making this one, so we label that as equal to 1. Okay, so here, this is that for the element. So element which is related to property. Okay, so then this 0 and 1, each of them which were corresponding to a column of that in the data. So that column of that in the data, which we were given that in the input parameters. Okay, besides that, we give the material property, we need to give the boundary conditions, is that right? Okay, the boundary condition, what we given that is given that into the node. Okay, we will have that in the majority of that in the location. All of that we label that as 0. Okay, labeled as 0, so which will correspond to a set of that in the data. Then, but add that in the input surface. So here, later we will put in that in an impact there. So we need to tell that where, so we put in that impact. Okay, we will label this part, so which is as equal to 1. Okay, just like that's in the top of that. So we label that's equal to 1. Okay, so then in that case, I will be able to apply the boundary condition. And for 0, I have that's free. I do not need to apply any of the boundary condition. Only for the case if we have that's equal to 1, okay, I will apply that's an impact of that node there. Okay, so this is that for the material property, for the node property. And then another one, which is related to, we just introduced that in the semi-ACAA. Okay, semi-ACAA, that's initially, so we do not put in the contact everywhere. We only put in the contact at that surface and at this surface. Then in that case, so for all of that, the other location, I can make that equal to 0. Only that at the initial of the contact for this part, I label that as 1 and label that as 1. Okay, so here, as I introduced here, this is that for the 3 dimension, you involve 3 sets of the data. So which is that the elementary property, the loading of the property, and then that's for the semi of the contact activation. Okay, here, that's obviously, if we wanted to label that by hand, yeah, it will be terrible. Yeah, so what we label that, we were using that in C++ of the code. Okay, C++ code. So each time we just slightly to change that in C++ code, then we can use that for the different of that in the purpose. Okay, so before we do that, we need to label this location. Yeah, so for this location, like that, for this part, if you do that by hand, it's very difficult as well. Okay, how we label this location? We using that in the graphic interface of the opticals, label this. Okay, so then let's go back into that's in the visualization. So using that's in the opticals. Okay, so here that's the I define of the sets here. So you will notice that here I define. If I visualize the set which I defined that in here. Okay, I define that in input phase. Okay, I make this window becomes smaller. Yeah, you can see here this one. Yeah, this is that's an input phase. Okay, this phase, which is legend, I will apply that's an impact here. So I need to know where I apply the impact. So you can see what I select is that I selected that's the node pointer here. Yeah, I think that if you are familiar with the opticals, it's very easy for you to know how do you select this and that's the location. Okay, I will not introduce this. Yeah, previously, I demonstrated how we do that in the previous of the presentation. So this is one of that. Okay, so then the other one is that. Okay, so I have that in the other of that in the input bar or the transmissions bar. I said so it's there is no point for me even insert of the cohesive element to deal with the contact interactions there. I only need to deal with the contact, such which is the interface. So then what I select in that I select in the load of there. So that's the insert bar. And then here, that's the transmissions bar. And then the rock sample, okay, rock sample, I need to add in this in the rocks into, I need to adjust the visualization. Okay, I'm making this. Okay, so I only need to, yeah, for the rock sample, yeah, I have that's initially of that's the contact, and that's the contact between the rock sample and the transmissions bar. Okay, so for this kind of set, what we define, which is here, you define that, which will reflect that's in the input file. Okay, if you look into that in the input file, that's what we defined there. So which will opticals which will be able to give you that in the set. Okay, so what is the number of that element is there? Okay, we needed this kind of information in that in the script, which is a C++ file. Okay, so now it's the time for us to open that in the C++ of that in the file. Okay, so what I do is that I just, okay, so the previously all of that I have that in here. Actually, I just copy so that previously the file we used to generate that for the dynamic of the BTS. Then we start changing, so then we can generate this, which is for the dynamic UCS test. Okay, I have already done that. Yeah, since his text sometimes is not a good idea for me to do that in this limit of the time. Okay, I have already done that. I show you that in the results. Okay, so let me find that in the folder where I save this. Okay, I open that in the script, a simple of that in C++ program. So previously I introduced this program many of the times. Each time we just did a few of that changing. So you look at that, what is that in the changing we made in here? Okay, so for this model, we have that in the total number of that in the element. So look at that in here. Okay, we have that the total number of the element, so which is equal to this one. So you just need to copy, so that data which is put in that into here. So then that's the total number of that nodes that you copy, that's the data. So then you put in that into here. Okay, so then other location you do not need to do changing. So then the next one, which is go to, so we say for the rock, we wanted to give that in property which is equal to 0. And that's for the loading plate. So we were given that equal to 1. Okay, you only need one simple of that sentence like this, you can get that. Okay, firstly, I have a loop, which is starting from the first element till that's the loss of the element. So for my case, I have the part, firstly, the part which is the rock. Okay, so initially I have that's the rock of that's in the path. Okay, if I have that's in the element label, which is smaller than the maximum number of that for the rock sample, then in that case, okay, so then I will get in that and label that. So I label that's equal to 0. Otherwise, I label that's equal to 1. Okay, so this 0 and 1, which will represent the material property. Okay, so let's introduce that. Okay, 0 and 1, which were represented that's here. Okay, we have these two columns. First column, then the second column. Okay, the first column, which is represented the material property for the rock. Okay, for the rock, what we needed to give? So we needed to give that lambda and u. Okay, lambda and u, as we introduced before, and for the lambda and u, so we can get in that from the elastic modulus and the Poisson's ratio. So previously we given that equation. Yeah, for u actually, so that's the shear modulus. So which is equal to E divided by 2 times 1 as that's the Poisson's ratio. Okay, so I'm not sure if that's the equation is correctly. Looking at our previous of the presentation, we given that in the formula how we can calculate the lambda and the u. Okay, besides that, we needed to give a damping. So this damping actually, so you can calculate it by the hand. We previously given that in the formula how we calculated this. Okay, we know, so we have this damping, so which is related to the elementary sets, related to that's in the elastic modulus, related to that's in the density. Okay, so this previous one, I given that in the formula to calculate this one as well. Actually, our program will automatically to calculate that one. So as long as in the control parameter, which you let in the program calculated that, so then the program which will equals this value. Since we know, especially when we using the graded meshes like that for the down of the sample, so we have that each of that in the element sets, which is vary so quite significantly. It will be difficult for you to give a single of that value. We for the software, if you let in the software to calculate it, so this is the viscous damping. So then the program which were based on the size, each size of that in the element. So then which were calculated in the viscous damping of that in the coefficient. Okay, then the other parameter, which is the homogeneity index. Okay, that's the same of the what in our RFPA code is that's the M of that's the value. Okay, so besides that, we say after that we will have that's the contact. Okay, we given that a contact penalty. Okay, here this is that we just using 10 times of the elastic modulus as what we introduced before. Okay, these two parameters which is related to damping, whether when we have the contact have damping. Okay, so here we didn't use this one. Yeah, it's according to what we introduced in previous, we put in that equal to 1.0 and that. Anyway, these two parameters actually is not use it. Okay, then the other one is that after that in the fail. So after that in failure, we have that in the suppose they will contact each other, which will have the a residual of the friction. Okay, so you needed to give that residual frictions of, yeah, actually, so this is a tangent of the phi, tangent phi CR. Okay, so that's the residual of that in the friction angle. Okay, so then that's the density. Yeah, so then that's the homogeneity index. Okay, so this is that given that for the tetrahedral of that element. Okay, so that's why what is we put in that in 0 and 1, that's the mean. Okay, then the next one, we given the boundary condition. Okay, the boundary condition. So what we given is that. So initially, what we have that in. Okay, we given a loop, which is the maximum of that number of that in the nodes. Okay, which is this one. We have that loop. Initially, we given that everywhere we given that in 0. So 0, which means that's free. 0, which is correspond to one column of that in the data. Okay, so 0 is free. Okay, we say we need to, for the split-Hopkinson bar, so we need to put in that, okay, we need to give that an instead of that waves there. Okay, for that node, so what we were given that, okay, so for that node, we copy that data. Okay, so looking at that here, we have an input file. Okay, this input file, which is just the set which we defined that using Hopkinson the graphical interface. So what I do, yeah, you can see here, the first one is I reading this data. So reading this data, yeah, as I said, yeah, Hopkinson's the structure actually, the data file, which is structured. So each line, you have that 16 numbers. So you can see, yeah, I have that, after I reading each of that 16 numbers, I transfer to the next line. Okay, I reading that in the, I reading each of that in the noding node. Okay, the noding node, yeah, for our case, we starting from 0 instead of 1, that's y minus 1. And here, that's I added this one. That's because I have this, the second part. For the Hopkinson, each of that in the part which is separately numbered. But for our case, we have that from consecutively numbered. So that I needed to add in that in the maximum number of that in the first layer of the parts. Okay, the first part we have that here. So this is the rock. Okay, looking at that in here. The first part we have that rock maximum of that node number is here. Then I add in this one. So that begin this one, I know this is that's in the notes of the Hopkinson bar instead of rock sample. So I reading this one, then I giving it a label. Yeah, I given that label that's equal to 1. Okay, so this one at that location, I will input in a waves here. I know. Okay, so then for the other location, we do not need to give any of the boundary condition. So then that's the O for that one. Okay, then besides that, we say we using that in semi-ACAA, which we given a flag. So if for the majority of the location, we given that in 0, so that means we only have the cohesive element there. So we do not need to do the contact calculation at the beginning. Okay, but we have that in, we say for the bar, okay, this is that's in the bar. Okay, so this is that's in the rock sample. And for the initial of that interface, this interface, we need to give that, let them have the initial of the contact. Okay, so what we do is that, okay, so we already define, so that's the rock of the initial contact of that's the face. And okay, so what we do, we firstly reading this one. Okay, reading this one, this data, looking at the formula we have it here, this have huge number of that in the data here. Okay, so how we do that? We given a keyword, given a keyword, then given a number. So what is this number? This number is means how many of the nodes is here. And for your case, actually, so as I said, it's easy for us to calculate that. Okay, we look at that, and although here that's have a huge number of the, we can easily to calculate that. So we say we calculate like in this. So we firstly look at that in the loss row for this one. Okay, for our case, we have that 128. So loss row. And then the starting of the row. Okay, we say this is that's number 5. Okay, we using this. So minus 5. So this is that's the number of the row. But since we calculated the start and the beginning, so then we needed to plus 1. Okay, then we have the row, which is 124. We say abacus data, each row, so which have 16, then you multiply 16. Okay, then that's the number. But you notice that for the last one, the last of that the row, so we didn't really, is not full. We miss a few of the data. How many we miss? 1, 2, 3, 4, 5, 6, 7, 8. Okay, we miss 7, 8 data. Then we minus 8. Okay, so then that's the number of that nodes in this set. Okay, so that's why I put in that number. So 1976, that's here. Okay, so then the remaining, so here, this is that's the same. Yeah, you follow this way to readings that's, then we given that a label. So that's equal to 1. Okay, here, this is the label given that equal to 1. Okay, only what I needed to remind you, since we have this is that's the node number, which is consecutively numbered. So for you to read in that in the second of that in the parts, so you need to add in that in the maximum number of the nodes of the first part, making sure you have that as the consecutively labeled. Okay, if we run this, okay, so run this, then you will be able to get in that in the input file, this part of that information. Okay, so. Okay, what we do is that to get this part of the information, velocity, animal property, and the node property, the boundary node flag. Okay, for that one, okay, let's run that. Okay, if we run this part, yeah, actually setting a number of the black pointer there. So you can use this black point to check whether you have that reading that correctly. Okay, so we directly go through that one. Yeah, for example, for the first one, so this one, what we are reading that's the this data. Okay, we are reading, so the first set, okay, you can, yeah, go through that. You can put in your mouse there. When it's run through, you put in mouse there, you can see it's reading that, the keywords, reading that, that's the number. Yeah, and so on. Yeah, then you go through, yeah, each of that, yeah, put in that in the break pointer for you to check and that. Okay, after the running, so then which we're generating that in the format. Okay, so here, this is that in the format. Is that in, okay, what you do, you just need to copy all of that in the information. So then you paste that in here. So that's what I get in this of that in the input parameter. Okay, after that, okay, so let me briefly to introduce, here I already introduced some of that. Okay, here, first one, we say this is that's in the material property. So previously we have the rock, which is labeled as 0, and the bar, we labeled that as 1. Okay, so this is that's in the material property. We already explained that. Okay, then the next one is that in the boundary of the property. Okay, the boundary property. So what we have that in the first column, that's 0, then that's the 1. Okay, the first column, yeah, actually it's given that it's 0 everywhere. So 0, that means it's free. Yeah, so, and then the first one, yeah, I initially needed to fix that. So then fix, I put in that in, equal to 3. Okay, so fix that, and so then I put in that impact there. Okay, so here I introduced before we have that 0, 1, 2, 3, and 4. Okay, 0 means that's free. We do not need to apply any of the boundary conditions there. 1, so means we apply a force there. If that's 2, means we apply that a velocity there. So sorry, if that's 2, it means we apply a gravity there. So the self weight, So G, if that's 3, or we apply a velocity. And if that's 4, so we apply a non-reflections boundary. So that's for the dynamic of the modeling. You need it using this boundary, which is called the non-reflections of boundary, especially for the Brostad modeling. Okay, later I will introduce one of that in the Brostad modeling as well. Okay, so that's in the note. Okay, then here, inside of the rock, we need to insert of the cohesive element. For the bar, it's unnecessary for us to insert in the cohesive element. For the bar, since we do not have that in any of the failure occur, what we focus on the rock sample. Okay, so that's we only insert in the cohesive element for the rock. Okay, cohesive element, that's in the cohesive element material property. Okay, what we need to give that material property for the cohesive element, we given a more cooling of that's in the shear strength. We given that a cohesion. So we given a cohesion. So we given a tension strength. So then we given an friction angle. That's typically to using the Cooling for the criteria. So you were given these 3 of the parameter. Okay, for the friction angle, what are we giving a tangent of the friction angle instead of directly to given this is the friction angle. Okay, besides this, we have that similar of that in RFPA. We have that M value. Okay, this is that M which is represented. Yeah, suppose here we using that in the homogeneous model. So actually here that's have no use. Okay, besides that, we need to put in that in the fracture energy. So as we said, we have that in the constitutive relationship which is like to this. Okay, so that's fair. So when we have that in the fair, so from here, that's the part. Okay, here we have that in the release of that energy. Okay, so that's related to G1 and G2. Okay, so this is that in G1 and G2. Yeah, so for this parameter, I say actually we given that in the based on the experience, we do not have a good way to determine of that in the G1 and the G2 as well. Okay, besides that, which is given that in the penalty. So we say for this case, we always given that 100 times of that in the E. Okay, then we insert in what I say, I given that material property here is that I insert in for the cohesive element. Okay, so you notice that in the previously, so we have that in the rock, we label material property, we label that's 0. Okay, so what I have this line is means I have that in a cohesive element. Here I have a cohesive element. Okay, this cohesive element will have material property label that's 0, and here that's 0. Then I insert in a cohesive element. This 0, which is represented, so this column. So this is 0 column. Okay, this is that material property. So that means I insert in a cohesive element, and that cohesive element, which is with the material property. So which is this one. Okay, so here, yeah, I will later when I will introducing the grain-based modeling. For the grain-based modeling, I will using this part which is significantly. So then it's easy for you to know how we using this part. So where I needed to insert in the cohesive element, and where I do not need to insert in cohesive element. Actually, for HFDEM code, we can insert in that, and that can what we are doing here. So we insert in the cohesive element. We can insert in here non-cohesive element. That means so you have that in the rock. If I insert a non-cohesive element there, so that means so just like in that in the PFC DEM of that in the code, of that in the unbounded of that in the border. Okay, so this is that in the input of that in the parameter. Okay, so then after that, okay, let's come back into to this in the component presentation. Okay, so then the next one, we needed to give the control of the parameter. Okay, the control parameter here actually, so this is exactly the same as that for the previously of the BTS test. So I do not need to do any of that in the changes here. I can directly to using the same one of the previous one. Okay, here this is the same as the previous. I do not want to introduce into that, so I introduce this into lossy time. Okay, I quickly, yeah, so skip this one. Okay, only since I do that in the change is here. Yeah, so I do not needed to, I needed to calculate both of the staples. Okay, so here I calculate that I totally calculated 300,000 of the staples. When I have that every 1,500 steps, I output in one of that in the data. And for this one, yeah, so we know for the BTS, we have a high of the strength. We needed to calculate more of that in the staples. Okay, so I calculated, I changed this actually, so I calculated the 80 or 800 of that in the thousands of the staples. Then I output the data, given that in every 200, 2,500 output. So then I will get a reasonable of that in the Philip pattern. Okay, so suppose we do that in the calculations. Yeah, so this is that in the same as that's in the BTS. So we do that in the we put in two, yeah, do the SHPB test. And for the monitor location, I do not need to change it as well. Okay, this is exactly the same as that for the BTS test. Okay, then we put in that in the impact in here. That's I already explained that. So this is that in the waveform, which we input. Okay, then we put in that in the monitoring of that in locations there. Okay, after that, we run that. Okay, so this is that in the run of the results, which looks like this. Yeah, I firstly show you that in the compounded presentation. Okay, here, when we have the stress wave portion to the sample, we have the sample which is highly loaded. So then after that, you will see that's in the failure which is occur. Yeah, so you will see here, that's the phone that's complicated of that in the failure pattern. And here, that's for the fragmented phones here. So we can even use that and you quantify that using the fragment size. We can get in the fragment size distribution. You can see initially, we only have a single of the rock with the formation of the crack. We found more of the fragment. And finally, we found that thousands of the fragments there. Okay, so then that's the stress wave of propagation. Okay, I show you that I already completed these calculations that yeah, putting that in the parallel. Okay, I already put in that here. That's in the visualization, the calculation in the, yeah, I have that in the calculations, but yeah, I put in that in here. I will replicate this on Tintin's computations as well as watching that for the dynamic of that in the UCS test. Yeah, but I'm not sure so whether that's be sufficiently to do the graphic card is powerful enough. I noticed that in the graphic card is do they do the static resilient the three-dimensional modeling and the dynamic resilient does not have problem. But previously, when I try to run the uniaxial complex for three-dimensional uniaxial complex for test on the computer, so that does not have enough of the memories there. Okay, so let's look into that. Yeah, let's look at that in the visualizations here. So in the that will be a little bit slow. Okay, so let's look into that on the visualization on the parallel view. Okay, we start in the impact, then we have that in the stress wave which is propagated here. Then you will see, yeah, so initially I skipping that in many of that in step here, you will see the gradient of that in the stress wave which is propagating through here. Yeah, when the stress wave propagation here initially, so you will see here that's have the macro of that damage. Since you have that's the stress wave approaching through here, initially, so you have that's the macro damage. And here, this is the macro damage. You look at that the damage value is D, so which is quite small, which is correspond to that 0. Okay, well, that's everywhere, so that's highly stressed. So you will see macro damage, so which is happening that everywhere. But although have that's the macro damage, so is not a form of the macroscopic of that in the crack. You look at that in the value here, that's almost equal to 0, so which is 1.2 multiple 10 minus 12. Essentially, so that's almost that's zeros there. Okay, so then you look into that when you have the red color, which is the appearance there, so that's the real of that's in the crack, which is the macroscopic of the crack, which is the appearance there. Okay, so then you will see here, which will have the formation of the cracks. Yeah, here, as I said here, which will involve that's very complicated of the failure of the pattern. Okay, so you will see here. Yeah, so here actually, so we do not have the experimental results since proven that since yet. So while we have that in the failure pattern, so which looks like so this. So this is very complicated. So what we plan to do is that based on the particle size distribution, which is compared with the experimental result, to get that in the particle size distribution. Yeah, you can see, so we do run many of that in the steps. So you were getting that. I think that I'm proud of that to say this is the only overcoded that can get into this. Yeah, so I have never seen any of that in the other of that results other using that a PFC or that's DDA, so are able to get in this kind of a failure of the patterns of the before. Okay, so this is that's in the visualization. So in the after you calculation, you can use that in Paraview to do the visualization. So you can also create that in the video here. So you can create the animation. So what I put in that in my PowerPoint presentation, actually, what is using the Paraview to present the animation. Okay, so then the last one I wanted to show you is that how that the results looks like. Okay, so the results is that I put in that into here. So the results for the dynamic of that in the BT, dynamic of that in the test is here. Okay, yeah, so that's they calculated the results. You can see here, this actually is that's in the VTK of that in the file. Okay, we have that in, since you have that in the, yeah, we separated the rock sample and that's in the split-Hopkinson bar, which visualized separately. Obviously, for the joints, we visualize that separately. So that's why here you see that's 3 group of that in the file. Yeah, so here represented the joints. That's represented that's in the Hopkinson bar, and then this represented that's a rock sample. And for that's in the particle size distribution, so each step after that's in the calculation, we output in that particle size distribution. So you can see here, that's initially, at the beginning we do the simulation, we only have 1 particle. So then at the end, okay, let's look at that. At the end, yeah, so I do that in the, yeah, so you notice that we have hundreds, okay, even thousands of that. And yeah, how many of that the particles here? So we have that finally. So one piece of the rocket, due to the dynamic test, we generated 4,331 of that in the fragments there. Okay, so this is that in the fragment size, and then the other one is that for this one. Okay, for this one is that we write an output of the file. So the output in file, which is called the this one, which is the stress edge string gauge. We say we have 2 of the monitor location. So the 2 monitor location. So if you open that file using the Excel, Okay, so Excel, so that's what it is that I show that in the component of that in the presentation. Okay, so how our results, which is from the experimental results, so that's I have that in the lossless slats. So we compare this with the experimental results. So this experimental results, which is from Monash University, yeah, which is Professor Zhou Jian's group. Yeah, it's Professor Zhou is that quite famous in the rock dynamics. And actually here we did that using both of that BCAA, yeah, and that's semi-ACA. And here for the BCAA, actually, which is long, takes a very long time. But for the semi-ACAA, yeah, for my computer, so which we're only taking that the one notch, will be able to complete the calculation. Yeah, I have that's the high performance of the computer. So for this one, this is the aroma of the high performance computer. I have that's the A100 of the graphic card here. And this one just taking a few of that hours, so which will be able to complete the calculation. Yeah, you can see here we have that reasonably agree well with the experimental results. Although, yes, you notice that in here, so we have some of that the difference. Yeah, but basically, so we have this corresponded well. Yeah, I think for your case, yeah, so if you do the dynamic of the BTS or UCS test, you can easily using that in the same of this model, you just change the input parameter using your input parameter and using your input waves. So then you will be able to model your experimental. So then together, so then you may be able to publish a very good quality of the paper. Yeah, okay, I stop here. Yeah, so I will stop that.